Students, good evening. Today I am going to solve one more problem. The problem comes under the category of steady state flow process. The problem is water at 90 degrees Celsius is pumped from a storage tank at the rate of 3 liters per second. The motor for the pump supplies water at the rate of 1.5 kilojoules per second. The water goes through a heat exchanger giving up the rate of 670 kilojoules per second and is delivered to a second storage tank at an elevation 15 meter above the first tank. Now the question is, what is the temperature of the tank delivered to the second tank? The pixelization of problem is given in this image. Now let us start to solve the problem. Okay students, let us start to solve the problem. The problem is pixelized. Pixelization of problem is given here. We have two tanks, tank 1, tank 2. The water present in the tank having its temperature 90 degrees Celsius. That means 363.15 degree Kelvin. In tank 1, the water is being pumped using a motor to a tank 2. On the way, it passes through a heat exchanger where 670 kilojoules per second of heat is being given up. That means this much quantity of heat is removed from the water. Now the question is, what about the final temperature? That means temperature of water in tank 2. This is the question. The height or distance between tank 1 to tank 2, the elevated height is 15 meter. Given data are density of water at 90 degrees Celsius is given, that means 0.965 kg per liter. Moreover, specific heat of water is given 4.184 kilojoules per kg degree Kelvin. And volumetric flow rate of water passing from tank 1 to tank 2 is given. Volumetric flow rate is 3 liters per second. Now I am going to solve the problem. The problem comes under the category of steady state flow process or constant pressure process. For this case, the total energy balance equation is del H, total changes in enthalpy, plus contribution by kinetic energy of mv square. So total change in kinetic energy change that is equal to half m del v square plus potential energy change mgz. That means mg del z is equal to the heat and work interaction during the process. Q minus Ws. Q stands for amount of heat added to the system or removed from the system, and Ws stands for shaft work. Okay, now I am going to find one by one. Before that, using volumetric data and the density data, I am going to find the mass flow rate of water. Mass flow rate of water. Mass flow rate is equal to mf, or mass flow rate of water is equal to volumetric flow rate into density. Volumetric flow rate into density of water. Volumetric flow rate is given. Volumetric flow rate is 3 liter per second into density is 0.965 kg per liter. Liter gets cancelled. The answer is 2.895 kg per second. This is the mass flow rate data. Mass flow rate is predicted. mfr is equal to 2.895 kg per second. Okay, what next? Shaft work. See, a motor is used to pump the water from tank 1 to tank 2. Okay, the motor needs 1.5 kilojoules per second. This much quantity of energy is supposed to supply to run the motor. The motor is used to pump the water from tank 1 to 2. So we understand that certain amount of work done on the system. Certain amount of work done on the system. Shaft work WS is equal to, since it is work done on the system, I am going to put negative sign. The answer is 1.5 kilojoules per second. Kilojoules per second. WS is predicted. Clear? Next, amount of heat added or removed from the system. See, in your question paper, it is clearly states that 670 kilojoules per second of heat is being given up. Clear? That means heat removed from the system. So amount of heat removed. Amount of heat. Since it is removed from the heat, it is minus sign, 670 kilojoules per second. Next, what about the contribution by potential energy? Potential energy P is equal to mg del Z. M stands for mass flow rate of water. Mass flow rate is nothing but 2.895 kg per second into gravitational constant 9.81 meter per second square into del Z. That means height between tank 1 and 2, that is 15 meter. Kg meter per second square. Kg meter per second square. This is called as Newton. 1 kg meter per second square is equal to 1 Newton. The remaining units are meter. One more thing is second. So Newton meter is nothing but joules. So the remaining thing is joules per second. The answer is 2.895 into 9.81 into 15. The answer is 425.99. Answer is joules per second. In terms of kilojoules per second, this is 0.4259 kilojoules per second. So contribution of potential energy to the total energy change. One more is kinetic energy. In this case, kinetic energy becomes 0 because there is no role of velocity. Clear? Right. Now, shaft torque is ready, Q value is ready, potential energy is ready, kinetic energy is 0. Now I am going to calculate the changes in enthalpy, total changes in enthalpy. Del H is equal to Q minus Ws. This term goes to this direction, minus mg del Z. The Q value is minus 670 kilojoules per second, and minus shaft of 1.5 kilojoules per second, and minus potential energy contribution. This is 0.4259 kilojoules per second. The answer is 600 minus 668.93 kilojoules per second. Now total energy change, total enthalpy change is predicted. In my previous class, for a constant pressure process, delta H or dH is equal to dQ. That means in a constant pressure process, the amount of heat added to the system is exactly equal to changes in enthalpy. In your heat transfer subject, you will be studied dQ is equal to m dot Cp and dt. dH is equal to m dot Cp dt. dt is nothing but difference in temperature T2 minus T1. T2 is the tank temperature of tank 2 temperature, T1 is the tank 1 temperature. Now I am going to find the value of T2. This is the question mark. dH value is minus 668.93 is equal to m dot. dH value is equal to kilojoules per second. M dot mass flow rate is 202.895 kilojoules per second into Cp value 4.184 kilojoules per kg degree Kelvin, and into T2 minus T1. T2 minus T1 is nothing but temperature 363.15 degree Kelvin. Okay, right. T2 is equal to minus of 668.93 divided by 2.895 kilojoules per second. This is kilojoules per second. This is kilojoules per second. One more thing is kilojoules per kg degree Kelvin. And minus of minus this term. This term, if this comes this side, this will be plus 363.15 degree Kelvin. Okay, wow. Kilojoules gets cancelled. Okay, the remaining thing is kilojoules per kg degree Kelvin. What is this? Kilojoules per kg degree Kelvin. What is this value? 4.184 kilojoules per kg degree Kelvin. Okay, wow. This is kg per second. This is kg per second. Once again, I am going to write this. So this is equal to minus 668.93 kilojoules per second is equal to mass flow rate 2.895 kg per second into Cp value 4.184 kilojoules per kg degree Kelvin into T2 minus T1 value is 363.15 degree Kelvin. Okay, wow. The kg gets cancelled. Kilojoules gets cancelled. Second gets cancelled. The remaining thing is this value Kelvin minus Kelvin. Okay, clear. Fuel consistency is okay. So T2 is equal to minus of 668.93 divided by 2.895 into 4.184 plus 363.15. The answer is minus 55.25 plus 363.15. The net answer becomes 307.92 degree Kelvin. The final temperature, or in terms of degree Celsius, 307.92 minus 273.15. The answer is 34.77 degree Celsius. The final temperature is 34.77 degree Celsius. Temperature of water in tank 2. This is the problem. Thank you.